So today we're going to dig into a really fascinating question that comes from a PhD dissertation out of the University of Calgary. And it's this: can we get our most powerful mapping technologies to work smarter, not just harder? It's all about teaching our digital eyes in the sky to have a much, much better conversation.
Our whole modern world, everything from the map on your phone to these crazy detailed 3D models of entire cities, it's all built by mashing together two amazing technologies: signals from satellites way up in space and pictures from cameras down here. But here's the wild part. For more than 30 years, the way we've been combining them is basically a one-sided conversation. It's this huge communication problem that's been hiding in plain sight.
So who are the key players in this story? Well, let's meet modern mapping's power couple, GNSS and photogrammetry. On their own, they're powerful, for sure, but together, they should be unstoppable.
Okay, let's break down what they each do. On one side, you've got GNSS. That's the official name for what we all just call GPS. Think of it as the ultimate navigator. It uses satellites to tell you exactly where you are on the planet, with incredible precision. And on the other side, you've got photogrammetry. This is the artist. It takes a whole bunch of overlapping photos, maybe from a drone, and stitches them together to build a rich, detailed 3D model of the world. So one tells you where you are, and the other shows you what it looks like.
And this is exactly why they should be the perfect team. The pinpoint accuracy from GNSS locks that beautiful 3D model from photogrammetry into its exact right spot on Earth. When it works, you get the best of both worlds: really high absolute accuracy, which means you know exactly where a building is, and super high relative accuracy, so you know the precise shape and size of that building.
But, like we said, this powerful partnership has had a fundamental flaw for a long, long time. It's a problem that goes back decades, and it's all rooted in this idea of a one-way conversation. And get this timeline is kind of wild. The basic way we combine these two technologies was figured out over 30 years ago. And today, we're still using pretty much the exact same technique. And the big problem is that the information only flows in one direction. The GNSS data basically shouts orders at the photo data, telling it where to go, but the photo data never gets to talk back. It never gets to say, hey, wait a minute. Based on what I see, I think we're actually a little bit off over here.
And this is not just some small technical issue. The author of the research we're digging into, Cameron Elam, he calls the standard method suboptimal from a science perspective, and, maybe more importantly, unwieldy from a practical one. In other words, it's not just flawed on paper, it's a real pain to actually use in the real world.
So what does unwieldy actually look like? Well, it's this clunky multi-step process. First, you have to process all your satellite data in one piece of software. Then you have to export all that data and go open up a completely different piece of software for the photos. And finally, you just dump those GNSS positions in as fixed points, basically forcing the photo model to fit whether it makes sense or not. It's inefficient, and you're just leaving a ton of potential accuracy on the table.
Okay, so this is where things get really cool. Instead of just accepting this 30-year-old method, this research basically went on a quest to find a better way. They came up with two brand new strategies to finally get these systems to have a proper conversation. And the two big ideas they came up with are actually pretty simple to grasp. The first one is what we can call the two-way street. You let the two separate software programs actually talk to each other, passing information back and forth. The second idea is even bolder, the one-stop shop. This is where you just build one single unified processor that understands both satellite signals and image data from the ground up. Two totally different ways to get to a smarter result.
So, the big question, right? Did it work? Did one of these new ideas solve this 30-year-old problem? Well, as it usually goes in science, the answer was a little more complicated, and honestly, a lot more interesting than a simple yes.
Let's talk about the wins first, because they were real. These new methods were a huge help when the GNSS signal got blocked, like a drone flying under a bridge. It could figure out where it was again way faster. In some situations, the photo data was so good it could act like a backup GPS base station. And it really helped stop errors from creeping in when the drone could only see a few satellites. These are seriously useful improvements.
But then there was the reality check. And this is such a great example of how science really works. Even though the GNSS positioning itself got better, that didn't automatically make the final map more accurate in every case. And why not? Well, it turns out the images from a typical aerial drone flight just had a little too much noise, tiny imperfections, to actually improve on the already super precise GNSS data. The conversation was finally happening, but one side was kind of mumbling, so it couldn't really correct the other.
And that's the big takeaway. Making one part of a complex system better doesn't always magically fix the whole thing. Real scientific progress is messy. It's complicated. So this work didn't find the one magic bullet, but what it did do was give us a much deeper, much clearer understanding of the real problem, which, is the critical next step.
Okay, so you might be thinking, this is all pretty technical. Why does it actually matter? Well, it matters because getting this smarter integration right is the foundation for pretty much the entire future of how our machines are going to see and navigate the world.
I mean, this is the kind of nitty-gritty research that leads to big things. We're talking about more robust drones that can map dangerous terrain without failing. We're talking about building those incredible 3D city models way faster and cheaper. And yeah, this is absolutely essential for autonomous vehicles that have to drive safely through cities where tall buildings block satellite signals all the time.
And that's really the heart of it all. All this complicated science and testing, it boils down to one simple but powerful idea that drives everything forward. Just having the courage to look at something that's been good enough for 3 decades and ask, you know what, can we do this better?
Which leads us with a final question to chew on. Our machines, our cars, our drones, our delivery robots, they need to see and understand the world more clearly and more reliably than ever before. So what do you think that next big breakthrough in mapping is actually going to look like?